Hope everything is ready. Welcome everybody to the virtual seminar of the International Institute of Physics in Natal. We are very happy to see here with us today Rodrigo Pereira, who is one of the researchers at the Institute, and he kindly agreed to give a talk at our seminar. So although we all know Rodrigo, I want to still give a small introduction. He received his PhD from the University of British Columbia in Vancouver, and he did a postdoc in University of California, Santa Barbara at Kavli Institute. And after that, he was for some time a professor at the University of São Paulo in San Carlos. And since 2016, I believe he is a member of the International Institute of Physics and a professor at the Federal University of Rio Grande do Norte. So Rodrigo works with condensed matter physics and strongly correlated electron systems. And more recently, he is interested in applications to topological topological quantum matter. For his work, he received some prizes, including the Humboldt Prize, the Bessel Prize of Humboldt Foundation in Germany. He spent some time in Germany working after 2017. So today he will talk about Kitaev spin liquids. So thank you very much again, Rodrigo, for giving your talk here, and the stage is yours.
Well, thank you, Dmitry, for the kind introduction. I'd also like to thank Thiago and Dmitry both for all the effort to keep the seminar going, and it's not easy. And okay, so let me first share my screen. And today I'm going to talk about some recent work that's where we looked at the possible signatures of Majorana fermions which are bound to one-dimensional defects in Kitaev spin liquids. I'm going to explain what they are. And so here's the plan. I'm going to start materials. And then I'm going to explain how we can get Majorana fermions as emergent excitations in a Kitaev spin liquid in a magnetic field in particular. And then we're going to focus on a model where we consider that there's some line defect in this material and ask about the physical consequences. And in particular, they're going to discuss the signatures in the nuclear magnetic resonance experiments that might have seen this gapless modes. And this is the work of my student, Lucas Freitas, and it's here in this reference. So Kitaev materials, the kind of materials you're going to be interested in, they're Mott insulators, which means we can think of the electrons as being localized in some positions on the lattice. And in particular, they are Mott insulators where the ions have strong spin-orbit coupling. So here are some examples. The iridates are among the most famous ones. And I'm also going to talk mainly about this one, which is alpha Rotinium trichloride. And for practical purposes, this material, you can think of it as magnetic ions, spins, which are localized on positions on a honeycomb lattice. So these gray circles here represent the position of the Rotinium ions. And if you ask about the electronic configuration of this Rotinium 3+ ions, taking into account that you start with 5 electrons in a d orbital, which are subject to a crystal field, as well as strong spin-orbit coupling. At the end, the low energy physics of the Rotinium ion can be described as a single electron or a single hole in this energy level, which has effective total angular momentum equals to 1/2. So we're going to describe this as spins 1/2, which are positioned on a honeycomb lattice. And actually, this material is, of course, three-dimensional, but what happens here is they have these layers of honeycomb lattices, which are piled up like this, and they're very weakly coupled. So we're going to describe this system as some kind of two-dimensional, stacking up two-dimensional honeycomb layers. And then the next question, once we understand that we have spins 1/2 on the honeycomb lattice, is how do these spin degrees of freedom interact? And here the strong spin orbit coupling is important because if you take into account virtual processes where the electrons visit the neighboring electron and interact, starting from a Hubbard model, you don't get the usual Heisenberg exchange interaction. So here we have to start from a generalized Hubbard model called Hubbard-Kanamori model, which includes the orbital degrees of freedom of these d orbitals, and also take into account the strong spin orbit coupling. So here I'm showing two of these neighboring Rotinium ions where the spins 1/2 leave, and they can talk to each other by some virtual process where the electron hops to the nearest neighbor Rotinium ion through some chlorine ion here. So this is the dominant exchange path, and here this would be on a bond which connects a dxz and a dyz orbitals. And this bond is perpendicular to what I'm going to call the z-axis of this octahedron. So I'm going to call this simply a z bond. And when you take into account that there are these two hopping paths here and derive the effective spin interaction generated by these virtual processes, you end up with this Hamiltonian, which I wrote down here, where the spin operators, now I'm writing them in terms of Pauli operators on each side of the lattice, and the spins talk to their neighboring spins via some interaction, which is anisotropic and bond dependent. So here, if I take two ions which are connected by a Z bond, like this blue bond here, they only interact via this Eisen type coupling, which involves the Z component of this Pauli spin operator. However, you can divide the honeycomb lattice in a way that each side has three nearest neighbors and label them X, Y, and Z. And the kind of interaction that you get is the total one is like this. So the interaction depends on the direction of the bond. If you take an X bond, you couple the X components of the spin operators. So exactly this Hamiltonian was written down by Kitaev a few years before it was derived by Kaliulin, starting from this macroscopic mechanism that I just described. And Kitaev proposed this model as some model that can host exotic physics because it's exactly solvable and it has Majorana fermions as elementary excitations, as I'm going to explain. But one way to anticipate that this model has some interesting physics is that it's actually a frustrated model where the frustration comes from this anisotropy in the exchange interactions. So if you think you are the electron or the localized spin that sits here on this site, and you look at your nearest neighbors, each nearest neighbors would like the spin to point in a different direction. So like here, these guys would like to order along this Z direction, but this one's along X and this one's along Y. So there's some kind of frustration here. So it seems possible that because of this frustration, the system might choose not to order magnetically in the ground state of this Hamiltonian. And this is what we're going to talk about. And I should say that what I described is just the dominant exchange path for these materials, but there are, of course, other possible interactions that would be perturbations to the Kitaev model here. And then these are going to play some important role later. But let's focus on this Hamiltonian as our starting point. So what we get from the Kitaev model, this Hamiltonian that I just wrote down, the idea here is that you can solve it exactly by fractionalizing the spin operators into a Majorana forms. So there is this representation where you write down each sigma operator on a given site as a bilinear of Majorana fermions. And there are 4 of them. There is 1 C and 3 B's, which I'm representing here. So it's like you're splitting your spin-on-half degree of freedom into the local Hilbert space of 4 Majorana fermions. They are Majorana fermions in the sense that they anti-commute and they are Hermitian operators that square to 1. And with 4 of them, you can represent the 3 Pauli operators. You can reproduce the usual C2 algebra. However, it's also important that this kind of representation has a gauge redundancy, because if you take on a given site and change the sign of all the Majorana fermion operators on the same site, because this is a bilinear, the spin operator, which is the physical operator, is invariant. So there is a Z2 gauge structure here, and also as a consequence of this Z2 gauge structure, the Hilbert space that you get from this Majorana fermions is actually larger than the physical Hilbert space of spin-on-half. I think that's like for Majorana fermions, you should get 2 complex fermions, so that would be like twice as large a Hilbert space. So to impose, to get back to the physical Hilbert space, you have to impose a local constraint that says that the product of all 4 Majoranas on the same site is equal to 1. And with this representation, you can then go back and plug this into the Hamiltonian for the Kitaev model. And the trick is that it's going to be exactly solvable because this model has a macroscopic number of conserved quantities. Because each spin operator is quadratic in this Majorana fermions, the exchange interaction is actually quartic, but you can separate the part that comes from the 3 beats defined at each site to define these variables, which is like this. You take 2 beats for neighboring sites, like I and J, and combine it into a single variable that lives on a bond. And I'm going to call this U's. And these are Ising variables that square to 1. And you can actually show that they all commute with the Hamiltonian of the Kitaev model, because each of these only appears on a single bond. And because these are now conserved quantities and their eigenvalues are plus or minus 1, you can separate them here in the Hamiltonian and replace them by their eigenvalues. And what's left is a Hamiltonian that is quadratic in the remaining C Majorana fermions. It's going to be convenient for us actually to define a gauge invariant conserved quantity, because these products of 2 B's they're not invariant under the Z2 gauge transformation, but you can define something like a Wilson loop that takes the product of these variables around a closed plaquette, a hexagon here. So I'm going to call this the Z2 flux operators, which also have eigenvalues plus or minus 1, and these are conserved quantities. And then once you fix the values of these conserved quantities, you get this Hamiltonian, which is exactly solvable. It's something that looks like a tight binding model for Majorana fermions on the honeycomb lattice, and you can get the exact ground state. And because it's exactly solvable, we know the answer. We know that the ground state has no long-range magnetic order. So in the absence of a magnetic field, the expectation value of the spin operator vanishes. So the ground state doesn't break any symmetries. Moreover, on top of this ground state, we get the excitations which are fractional, in the sense that the spin degrees of freedom break up into Majorana fermions. And this is an example of what we call a quantum spin liquid. So the Kitaev model provides an example of an exactly solvable model with a quantum spin liquid ground state. And the story gets even more interesting if you add the magnetic field, because first of all, if you in the absence of a magnetic field, you can compute the spectrum for this C Majorana fermions that are now going to move on top of this flux background. And in the ground state, you can fix the eigenvalues of the flux operators to be all equal to +1. and you compute the spectrum of the C-Majorana fermion moving on a honeycomb lattice, it looks pretty much like the spectrum of graphene in the sense that at low energies, you get a Dirac cone. So it's like the spectrum of a massless Majorana fermion here. But if you add a magnetic field, you can show that breaking time reversal symmetry generates a mass term for this Dirac fermions. And this mass that it generates is very similar to what happens in Haldane's model for the quantum Hall effect without a magnetic field. So it's a non-trivial mass term. It's topologically non-trivial because you can compute the Chern numbers, the topological invariant for these bands of Majorana fermions, and they're non-zero, equal to plus or minus 1. So this gives us a quantum spin liquid ground state, which is topologically non-trivial. It has this non-trivial bands of Majorana fermions. But besides the C fermions, for which we know the dispersion, there is another type of excitation in the spectrum, because I said I fixed the flux to be +1 in the ground state sector of this model, but you can also change the flux variable to be -1 on a number of these hexagon plaquettes. And I'm going to call this type of excitation a vortex of this Z2 gauge field that emerged from the fractionalization of the spin degrees of freedom. And here it's interesting that single vortices can bind zero modes of the Majorana fermions, which are topologically non-trivial. So what you get here is some kind of a bound state, which is it's going to be this Majorana zero mode in the spin liquid. It's very similar actually to the physics of topological superconductors, except that here all the fermions and the gauge fields that trap this the vortex that traps the Majorana zero mode are all emerging from fractionalization. And this is this phase, the Kitaev spin liquid in the magnetic field is a topological phase. So it has a lot of interesting properties. So, for example, in the bulk of the material, you can have this zero modes bound to vortices, and you can show that these Majorana zero modes are very much like in other topological superconducting phases. They are Ising endians. So the idea is that if you're in a sector where you have these vortices fixed at some positions on the lattice, and you have a zero mode bound to each of them. So the ground state sector in the presence of these vortex excitations is going to be degenerate. And the number of ground states in the sector scales exponentially with the number of vortices that you have here. And if you do some kind of operation where you change the positions of these vortices, moving one of these Majorana zero modes around each other, you're going to perform some unitary transformation in this low energy subspace, which can be represented in terms of these Majorana operators in this way. So this is what we call braiding, and then it's the whole idea of the topological quantum computation, that this kind of system forms a higher dimensional representation of the braiding group. So the idea is that performing this kind of operation, you can implement unitary transformations in this low energy subspace, which is automatically or intrinsically protected against decoherence because of the topological properties of this system. And moreover, another hallmark of topological phases is that you get interesting properties at the boundary of the system. So here, in this case, we're going to get gapless edge modes, which are chiral and run in some specific direction. And these are chiral Majorana modes. So some time ago, we actually made a proposal for how one might try to implement this braiding operation, assuming that someday you have this highly controllable Kitaev spin liquid, ideally a single layer of a Kitaev material, and you might want to create vortices that trap Majorana zero modes at specific positions and move them around each other to implement these operations. So, and you propose that this could be done with electric fields, which sounds counterintuitive because here I'm talking about a system which is a magnetic insulator. So you think that it doesn't have any electric response at low energies. But the idea is that we can show that local electric potentials can modify the Kitaev interactions in the vicinity of the point where you apply this electric potential. So we are modifying the exchange couplings somewhere on the lattice is going to modify the energy for creating one of these vortices that traps the Majorana zero mode. And actually applying a voltage, like a constant bias here, V0, lowers the energy of the vortex excitation, is what this line represents. So if you already have some vortices in your system, they would end up being attracted to the points where you apply this electric potential. And if you can move this, here is thinking of some scanning, tunneling microscope tips. If you can move them very slowly, you should be able to carry the Majorana zero modes adiabatically just by varying the position of the tips. And then, of course, the question is, do we have such materials? What's the experimental situation? And there has been some evidence that some kind of Kitaev spin liquid physics is found in Rotinium trichloride. First of all, at zero magnetic field, here I have some kind of phase diagram as a function of magnetic field and temperature. And what one sees that low magnetic fields is that this material actually orders is in some kind of phase with long range antiferromagnetic order is called a zigzag order. And that's because the complete model for ruthenium trichloride is not just the Kitaev model. It contains perturbations, including the Heisenberg interaction itself. And these perturbations are strong enough to take the material away from the Kitaev spin liquid phase. So it does order at low fields, but then what experiments show is that if you apply a strong enough magnetic field, you can actually suppress the zigzag order. And here in some regime of magnetic field around 8 to 10 Tesla, there might be something that looks like a Kitaev spin liquid. And one piece of evidence that got a lot of people excited was the experiments that measure the thermal Hall conductance in Kyoto a few years ago. What they saw is that if you have some heat current here flowing through the material, and you can actually also measure the transverse temperature gradient. So you can define something like a thermal Hall conductance analogous to the thermal Hall to the Hall conductance in the usual quantum Hall effect. And then you measure this thermal Hall conductance, the value that comes out in some range of temperature and magnetic field around here is very close to a quantized value in proper units here of a quantum of thermal Hall conductance, but the quantized value is 1/2 what you would expect from something like an electron or a complex fermion. This value 1/2 is exactly what we expect from a chiral Majorana edge mode. More generally, this value would be identified with the central charge of the 1D system at the edge. And they also saw some interesting dependence with the direction of the magnetic field, because this value here can be related to the Chern number of the bands for this C Majorana fermion that I was talking about before. It's actually possible to change the Chern number from +1 to -1 by varying the direction of the magnetic field. And then what you see is that the sign of the thermal Hall conductance also flips. But not everything is clear at this point. There are some discrepancies. Most famously, perhaps, there has been this experiment here, recent experiment by the group at Princeton, where they also looked at the the longitudinal thermal conductivity and saw a very clear signal for quantum oscillations in the conductivity as a function of a magnetic field, which is something that you normally associate with metals. But here we're talking again about insulators, and the Kitaev spin liquid in this range of magnetic fields is expected to be a gap phase. So there are some contradictions there. This is still to be understood, and I'm not going to try to offer an explanation for this experiment, but I want to focus on something that another sort of controversy that motivated our work, which is this Nmr experiment that measured the spin lattice relaxation rate in ruthenium trichloride, precisely in this range of fields where one expects to find the gapped Kitaev spin liquid phase. But they saw a dependence of the spin lattice relaxation rate with temperatures at low temperatures, which is a power law. Here, this is a log-log plot, so from fitting the data here, you can extract an exponent, and they say that the spin lattice relaxation rate scales like temperature to the cube. And quite generally, what you see from the spin lattice relaxation rate is sort of a measure of the low energy density of states for so like sort of probes the degrees of freedom at low energies to which your nuclear spin is coupled and by means of which it can relax. And what you would expect usually from a gap phase is some kind of activated temperature dependence like this, which 1/T1 should become exponentially small if you have a gap to spin liquid. But they said that it's actually a power law, which is more suggestive of a gapless phase. So I'm going to come back to that experiment, but let me start by describing to you this model that we studied, which includes line defects in Kitaev materials. So defects are always important in the description of real materials. And in particular, when you talk about Kitaev materials, there has been a lot of interesting work on the effect of this kind of disorder, like vacancies and bond disorder. They're particularly important for this iridate here, because it contains hydrogen, which introduces, occupies some random positions on the lattice and introduces some significant degree of disorder. But these are like zero-dimensional or point defects. And I want to consider line defects, which can be of different kinds, like dislocations in grain boundaries. The specific kind is not going to be very important for our model. And the reasons that we think this might be important or interesting as some kind of a way to perhaps control the properties of this material, it might affect the low energy properties. So for instance, it has been shown that one-dimensional defects or these line defects can be engineered in two-dimensional materials. So here I'm showing the transition method dihydrocogenide, where you can actually bombard some region in the material with electrons and create some defects along the line because of the vacancies tend to cluster together here. So you form this line, which you can see here in the experiment, where the atoms are a different distance from each other. Moreover, actually, these 1D defects might already be there in the three-dimensional crystal, because we know that ruthenium trichloride, like many of these layered materials, they are made of stacking of two-dimensional layers, which are very weakly coupled by van der Waals interactions. So what happens there is that you could have this kind of defect known as stacking faults, where there's some kind of sliding of one layer on top of each other, so the atoms fall on the wrong positions. And sometimes you have this would represent like the next layer on top of this one, which is represented on dashed lines. And here you have a region where the atoms are stacked in one way and here in a different way. So these two regions, they're separated here by a line where the atoms are further from each other. So these line defects actually separate the two regions of stacking faults. And here's the model we are going to consider. We're going to model this line effect as just by taking the Kitaev model and weakening the Kitaev interaction along the line in the honeycomb lattice. As in a way that we have J is going to be the exchange interaction parameter in the bulk, and the one along this line is going to be some J tilde, which is weaker than J. And we're also going to include the magnetic field, so it's initially with the Zeeman coupling for the magnetic field in some direction that we can vary and play around with this orientation of the magnetic field as well. And you can define, just to parameterize this angular dependence, I can define the usual polar angle here with respect to the z-axis, which a ruthenium trichloride is defined by the octahedron of chlorine atoms around each ruthenium. And then the question is, how can this line defect change the physics of Kitaev spin liquid at low energies? To understand what's going on, it's useful here to start from a limiting case where you just set this J3, or the coupling along the line effect, to 0. And in this case, it's like I break the bonds along an entire line and separate the two regions of the Kitaev spin liquid. And remember I said this is a topological phase, so if you have an edge, which I now do, you're gonna have edge modes, chiral edge modes that run along the edge here. And so the starting point in this case is that you have gapless one-dimensional modes running along these lines, localized at the defect, one on each side. And because I broke this bond here, in this case, they're blue bonds, I'm calling them Z bonds. Because I broke the Z bonds, the BZ fermions, which were initially absorbed into the Z bond, the Z2 bond variables from a gauge field, they are now set free. But here, along this defect sites, they're going to appear in the Zeeman coupling. This is going to be important. So I can again represent the sigma Z operator for all the sites as bilinear, something that couples the BZ fermions with C fermions, some kind of hybridization of Majorana fermions of different flavors. That's what the Zeeman coupling does. And I'm going to do this along this line of defects. And all the other BZ fermions, they're just absorbed into the conserved gauge variables, and they're frozen out at low energies. And the main question here is, do these gapless modes survive coming from this limit if I put back the coupling between the sites, weak coupling between the usually a quantum Hall state, and these will be chiral edge modes of electrons. Once you turn on any coupling between edge modes, they're going to hybridize by tunneling. So you end up gapping out these one-dimensional modes along the edges. But here the story is going to be different. It actually has to do with the fact that the fermions we're talking about they're emergent from the fractionalization of the spin degrees of freedom. And there are restrictions about the kinds of coupling that we can write down here in the effective theory. And there is actually no tunneling between Majorana fermions from different spin liquids. Okay, so now we're going to start from this model, and to make progress, I'm going to make some approximations here. The first one, so I'm going to consider that the coupling at the defect is weak. Also, the magnetic field itself is small compared to the exchange coupling in the bulk. And the first approximation we're going to do is what everybody does, like Kitaev did it in his original paper. We're going to replace the effect of the magnetic field, which actually breaks the integrability of the Kitaev model, by an effective operator. It also breaks time reversal symmetry, but we replace the Zeeman coupling by an effective 3-spin interaction. There appears a third-order perturbation theory in the magnetic field. And this third order perturbation theory generates the kind of second neighbor coupling of Majorana fermions that I mentioned before, which is similar to the Haldane model on the honeycomb lattice for electrons. This is what accounts for the non-trivial mass term in the direct theory. And so, yeah, so we're gonna take this and I get from the perturbation theory in the magnetic field the second neighbor coupling for the C fermions, and this kappa here is third order in the magnetic field. For it to be non-zero, you actually need all three components of the magnetic field in the axis that I defined before to be non-zero. And this sets the mass gap for the C fermions. Also at the line defect, we're going to keep the projected Zeeman coupling, which means that I'm going to allow this H, the Z component of the magnetic field to be comparable to the weak coupling J tilde. So there, along the line defect, I do not completely get rid of the magnetic field term. We're going to keep this projected one. And with this, the effective Hamiltonian for the low energy physics here, for this lattice model, ends up being like this. So we have H0 here contains all the usual terms from the solvable Kitaev model, which are written down as quadratic terms of the C fermions in the bulk. All the B's are frozen out in the conserved gauge variables. Here at the line defect, we keep the J twiddle term in terms of the dynamic BSV and C Majorana fermions. So this one is an interaction, it's quartic in Majorana fermions, and we keep the projected Zeeman coupling. And in the presence of both these terms, this model is not exactly solvable, and they're actually going to compete with each other. And the way we go about this is the way we're just gonna try some mean field decoupling of the effective of this interaction here. So I defined some mean field parameters, which basically prove the hybridization of Majorana fermions of the same type from different sites, so across the defect. So there's a chi-B and chi-C. Whenever one of them is non-zero, the other one is going to be non-zero as well from the decoupling of this term. And when this happens, what this means is that you hybridize this Majorana fermions from different sites, and then you should gap out the one-dimensional Majorana mode that you had at the beginning. And then we do the usual mean field theory. We derive some self-consistency equation for these other parameters. And we find that if you fix this magnetic field to be non-zero, the Z component of H to be non-zero, the self-consistent values of the order parameters, they vanish identically below a critical value of the exchange coupling, this J twiddle. So here, this is the value of the order parameters as a function of this weaker coupling at the line effect. And for a particular value of the magnetic field, which here we're fixing along the 1-1-1 direction, which is perpendicular to the plane of the honeycomb lattice. And you also see that above this critical exchange coupling, the values of the other parameters increase continuously. So this is some kind of continuous phase transition, but just for the boundary degrees of freedom of this model along the line effect. So it's a difference in the spectrum of this defect one-dimensional mode, if you like. And if you, in this regime here, where you have the values of chi-B and chi-C, the order parameters calculate itself consistently, you can plug them back into the mean field Hamiltonian and compute the gap for this one-dimensional mode, and this is the result here. So you see that above the critical value, which for this magnetic field is around 0.15 in units of J tilde of J, and then the gap increases smoothly above this critical coupling. And you can see the transition by looking at the spectrum. Here, this is the spectrum as a function of the energy, the dispersion of the spectrum of these modes as a function of momentum along the direction of the defect. So you have a continuum which is dissociated with the bulk modes, but you also have here some modes with linear dispersion. These are the gapless modes at weak coupling. So starting from j till equals 0, what we see is that this mean field order parameter is going to remain 0 up to this critical value, and then the spectrum remains gapless, but above the critical field, you gap out this one-dimensional mode. And then we looked at the dependence of this critical exchange coupling on the magnetic field. So first, if you fix the direction of the field, but vary its magnitude, you can get this dependence here, which you can fit to find out that the critical coupling scales like the absolute value of h to the power 3. You can also look at the direction, the dependence on the direction of the magnetic field for a fixed magnitude. So here we are varying the angle of the magnetic field starting from the z-axis along the line that includes the 1, 1, 1 direction. So you see that there is some peak here for an intermediate angle. And actually the values here for theta equals 0 or pi over 2 are the extreme values where the magnetic field is along the z-axis or in the xy plane. So at these values, what happens is at least one of the components of the magnetic field vanishes, and this implies that the parameter kappa, which I defined before, vanishes as well. And that sets the mass of the Majorana fermions in the bulk. So unless the gap in the bulk vanishes, we find that this critical coupling is always finite. And once we have convinced ourselves that there is critical exchange coupling, we can derive an effective low energy theory in this regime with the gapless modes along the defect. So we just go back to our mean field Hamiltonian, which is quadratic in Majorana fermions. We can Fourier transform it and define this complex D fermions now, and calculate this matrix A here, which diagonalizes the mean field Hamiltonian. And if we focus at low energies here, which means modes around Q equals 0, and we can expand the Hamiltonian to lowest order, to first order in Q, and then Fourier transform back to a real space to define an effective theory in the continuum. And this is the low energy effective Hamiltonian, which now only includes the gapless modes in this regime. So it has become an effectively one-dimensional theory. We projected out the bulk modes and the two-dimensional modes which are gapped. And then we just have one chiral Majorana mode, which is the right mover, and another which is a left mover. And the velocity here that sets the slope here in the spectrum is something you can determine analytically in terms of the parameters of the lattice model. It depends in particular on this parameter kappa, which determine the mass of the bulk modes. And besides the effective Hamiltonian, we can also derive the representation of the spin operators in the low energy theory. So it's basically you have to project the original representation of in terms of the B and C Majorana fermions onto these low energy modes, which are the chiral Majoranas. And it's going to be a bilinear again of these Majorana fermions. So here sides, the way I'm writing this, side J has a projection. If I take this side here, which is sitting exactly at the line defect, so it has a projection onto the low energy mode, which is moving to the right. And across the defect, there is another side which projects onto the gamma left mode. And here also you can fix the prefactor of this projection in terms of the parameters of the lattice model. And an interesting technical detail here, which is actually important for the physics as well, is that this low energy representation of the spin operator has to be quadratic when written in terms of this chiral Majorana modes. And because gamma squared is just equal to the identity, the leading representation of this operator must include some derivative here somewhere. So it's a gamma dx gamma. And this is with the representation of the spin operator. And if you plug this back into the interaction, the weak exchange interaction J tilde across the defect, which couple these two spin operators, in the effective field theory beyond the mean field approximation, we include now this quartic term, which actually has these two derivatives. So if you do some power counting here, this operator comes out irrelevant in the renormalization group sense. So our fixed point Hamiltonian, we just had this gapless one-dimensional Majorana modes, is actually stable. The leading perturbation allowed by symmetry here is irrelevant. And that helps to understand why there is a critical coupling, critical value of J tilde, below which the spectrum remains gapless. This operator is only going to gap out the spectrum when this the prefactor here becomes of the same order as the velocity of the Majorana fermions in the unperturbed Hamiltonian, our fixed point Hamiltonian. And it's also interesting to note that this is now effectively a one-dimensional theory, and the same kind of theory shows up in purely one-dimensional models. So you could start with a model which just has Majorana fermions on a chain with four-site interactions. And if you take the low energy limit, you end up with this kind of interaction as well. So this was discussed in these papers by Ramani, Affleck et al., and also in this paper by Asen and Jason Alicia's group, where they show that this is the leading irrelevant operator. And from this perspective, you can also understand and say more about the critical point above which the gap opens up. And there it's understood that beyond the infield level, this critical point is described by the conformal field theory of the tricritical Ising model. Okay, so now we have this effective field theory for the low energy physics of these modes which are bound to the defect in the Kitaev spin liquid. So we can go ahead and ask about the physical consequences of where would they show up. So we wanted to think about some kind of experimental response that probes the low energy spectrum. It has to be local because you want to think about the spins which are very close to the line defect. So we turn to the spin lattice relaxation rate, which I mentioned before, which essentially probes it's like a relaxation rate for how you start with you polarize your nuclear spins, and you ask about how it relaxes to the unpolarized configuration. And the way it does so is by interacting, the nuclear spin interacts with the electronic spins, which live in the Rotinium sites of Rotinium trichloride. So that's the experiment that has been done. And within linear response theory, you can relate the spin lattice relaxation 1/T1 to the dynamical spin susceptibility. So here it's written in terms of a dynamical structure factor for the spin components, which are perpendicular to the direction of the magnetic field that we applied, which are in general different from the directions of defined by the octahedra here. So there's some rotation involved between the different bases. And in our theory, we can then project the spin operators onto the chiral Majorana modes, the gapless modes, and write them like this, again as a bilinear of the gapless Majorana modes. And with this, we can relate the calculation of the spin lattice relaxation rate to some green functions of non-interacting Majorana fermions, which we can compute at finite temperature at this fixed point where the Majorana fermions are non-interacting. And what comes out of this calculation is this dependence T cube, which had been seen, as I mentioned before, experimentally. And here it's interesting to note that this T cube dependence comes from the representation of Majorana fermions, of the spin operators in terms of Majorana fermions, including the derivatives. You can go back and do some power countings and see that the 3 here has to do with the derivatives that we had back there. So so it's not just a factor of density of states. It has to do with the fact that we are representing our spin operators as Majorana fermions. So it's some kind of indirect signature Majorana fermions at the line defects. and we're actually proposing this as some possible explanation for this experiment. If you accept that the sample of ruthenium trichloride has some low but finite density of line defects, and it's possible that the spin lattice relaxation rate is going to be dominated not by the bulk modes, which are gapped, but at low temperatures is going to be dominated by the spore law contribution coming from the gapless modes bound to line defects. And yeah, so yeah, this is just to contrast the representation in terms of Majorana fermions with something that you would write down representing spins, like fractionalizing them into complex fermions, something like this. And then here there are no derivatives, so you actually predict lower exponent for the spore law dependence. So again, so this has to do with the Majorana fermion representation. And with that, I will conclude. So basically, the idea is that in these Kitaev materials, you have this emergent Majorana fermions, and we are proposing that these gapless modes that can be bound to one-dimensional defects are quite robust, in the sense that there is a finite exchange coupling for gapping them out, and that has to do with the physics of the possible interactions, the ones that are allowed by symmetry in the system of emergent Majorana fermions. And this might explain the cubic temperature dependence observed in some NMR experiments. So thank you.
Okay, thank you very much, Rodrigo, for this very interesting talk. And let us see if we have any questions. So please raise your hand in Zoom or write your question in the chat. Maybe I'll start with my questions first. When I heard your short version of this talk, I had some questions, but you partially responded to it in your talk here. So this is about the interaction of edges, in particular in quantum Hall. So you said that if you have an interaction of edges in quantum Hall, then you generally break the topological order because of hybridization of zero modes, of edge modes, right?
You gap out the edge modes immediately, right? Because of tunneling. So it's like you turn your two subsystems into a single quantum Hall state.
So what does it mean? So does it mean that you do not have any edge modes in this case, or because I naively thought that in some way you can also organize braiding using tunneling in quantum Hall.
Right. So let me go back to my figure here. Where is it? Here, right? So actually, what we imagine instead of liquid, I had two Hall states like this, and I drew the, let's say, this direction are the edge modes, but actually running around the entire system, right? So like this. If they're really decoupled, so you have two different quantum Hall edge states, but then if you turn on tunneling, what happens is they become a single system, right? So like you glue them together, we still have an edge mode, which is now running around the entire system, right? But if you probe the spectrum locally, which was what we're doing here in the bulk, then what you see is that this local dynamic response is gapped. But still there is some gapless mode somewhere else.
I see.
Is that what you had in mind?
Yeah. And I'm not sure there's a good answer to the following question, but is it clear why in this particular system, in the Kitaev spin liquid, you have a different situation?
It's because essentially I'm not allowed to write things like, I was calling them, so say right and left here, right? I cannot put this gamma right, gamma left coupling directly in the Hamiltonian with one Majorana fermion from each side. Because the local spin operators, the physical operators from each side of this defect has to have two Majorana fragments. So the leading coupling allowed by the constraints on physical operators and by symmetries must be quartics. So that's the difference from the tunneling term, right?
I see. So maybe like another short question is about this cubic behavior in temperature.
Yeah.
So do you conclude that in this case it's the defects that are responsible for this cubic behavior, or is it just edge mounts that contribute?
I would say, let's say one possible explanation is that there is a finite density of defects, of these line defects in the material, right? It must be a finite density, not just one edge mode, because it's like a bulk response. So you need a significant number of nuclear spins which are sitting close enough to the gapless modes so that they pick up this contribution to 1/T1. Right, so because these nuclear spins are all over the place in the sample, they're just not near the edge.
So the experimentalist should somehow find a way to control the number of defects and see.
Yeah, that would be ideal, right? You can put them where you like, and then like the experiments on a single layer that I showed, and then you can measure the relaxation of a nuclear spin or some other kind of qubit, and you know where it is, and that would be like the way to really clarify this.
Okay, thank you very much. We have another question from Fabio. Fabio, please go ahead.
Thank you, Dmitry, for the word. Rodrigo, nice talk. Pretty good physics. Let me do two questions, right? The first one is about the behavior of QB and QC. As you are showing in this slide, you decoupled in a mean field treatment, and when you evaluate them, they show different behaviors. One behave in a positive way, and the other in a negative way, right? Why does happen? And they vanish identically, as you said. Why does happen? Because in your decoupling, we can't anticipate this kind of behavior. We see that QB is positive and QC is negative. Why that? Why this?
Well, you can anticipate it from here, because the Kitaev coupling here is positive. We're taking ferromagnetic coupling, and there are factors of I here, right, in the definition of this mean field parameter. So it's such that the Chi-B and Chi-C are real numbers. You can check here from the properties of the Majorana fermions. So this would be like if you put in the factors of I here before you do this mean field decoupling, so this would be like plus I here. So the system will benefit from this term energetically when Chi-B and Chi-C have opposite sides, one positive and other negative. Which one is which doesn't really matter. But the way you start the self-consistency equation in mean fields, just select this choice here.
Please, because right, I missed some point in your explanation because you spoke different. Look, in one second point, when you spoke about the electric potential changing the behavior of the spin in your first slides, When you wrote down the Hamiltonian, the Kitaev Hamiltonian, if I missed, it doesn't contain the potential, the electric potential in your first slides. And yeah, no, in the beginning of your talk, when you showed that nice picture, yeah, this one, the last you showed.
Which one?
With your PRL of 2020.
Oh, okay, sorry. Yeah. Just give me a second.
Okay,
Yes.
I can wait. Yeah, this one. When you wrote down your Hamiltonian, in the beginning, you wrote the electric potential, or during your mathematical steps you included?
Right, so actually I did not even write down the Hamiltonian to which we add up and add the electric potential, because that must be the Hubbard model, right? So actually the Hubbard-Kanamori model, from which the Kitaev model is derived. So the J comes from perturbation theory in hopping, right? So T squared over U kind of thing. So to get the kind of effect that I'm talking about here, I have to go back to this Hubbard-like model and then add the local potential that couples to the local electron density. Then there you have the density operators, and then rederive the spin Hamiltonian at low energies. And that's how this V naught modifies the exchange couplets.
Right, but look, usually when the electric potential in connection with the electric field affects the spin degrees of freedom, you associate with the magnetoelectric effect, right? With your topological orange. In your system, you have this kind of physics?
It's similar kind of idea, but talk about magnetoelectric effect, you're thinking of some magnetic phase
Focus
which
channel,
is
and my name is
right?
Paul.
And
Thank you for watching and have a nice
fields.
day.
Here we're applying the similar mechanism to a spin liquid.
Portuguese
So
sound
you
like
don't
Russian.
have you cannot have this classical picture of frozen
So why
magnetic
am I even
moments that you
asking
can
that question?
try
Well,
to control with
people hear
electric fields.
Portuguese, and it's
But
usually
the idea you can actually control the
Brazil or
excitations
elsewhere, and they
of the
think it
quantum
sounds
spin
Russian
liquid
or
with
Slavic.
electric fields.
Russian being a Slavic language, of course. Most of the people who
Right.
say this are
Thank
people
you
who
for your
don't
answers.
speak either.
Thank you.
There is a question also from YouTube. So some of our participants, they are watching a YouTube transmission of this seminar. There's a question from Luan Martins, a student from Federal University of Alagoas. And the question is about this, the mean field approximation. As far as I understand, he wants to know a little bit more details about how this was used to derive the results.
So let me go back to the equations. Yeah, so here it's the difference from the usual mean field approximations that you use for spin systems, say like for the Ising model, like the Vine. The field decoupling you do is in terms of the Majorana furnace. But other than that, the idea is to turn your interacting Hamiltonian into an effectively non-interacting one. So here you do this decoupling of the quartic terms in all the possible ways here. So for instance, there is one where you replace these PB operators by the expectation value, and then you get some quadratic term for the C's, which depends on the expectation value of this one. And this is the chi-B I defined below up to these factors of I. And then you can diagonalize this quadratic Hamiltonian for the fermions, compute a spectrum, compute the ground state energy, and impose self-consistency at the end, right? Because these order parameters have to be computed as expectation values in the mean field and ground state. So there's some self-consistency there. And then the idea is that you find out that the order parameters remain zero if J2 is small enough.
Okay, so I hope this answers the question of Luan. Let's see if there is any other questions. So maybe one last short question is whether you think that this edge modes in this case somehow may be helpful for quantum computing, and any ideas of how to use them?
Use them. Actually, I think ideally you'd like to get rid of them. The question here was more like, well, how do you affect the physics, right? Because if you're thinking of making a topological quantum computer out of Kitaev materials, you'd like to have a fully gapped system, a single layer where you can put your vertices with Majorana zero modes or you control. But if you have this, not only the edge modes, but this one-dimensional gapless modes running along the defects, that could disturb the manipulations that you want to do with your gap excitations, right? So it's
they may be somehow useful on their own.
Yeah, I don't have any concrete ideas for how they could be useful.
Okay, so
they're 1D modes. There's some kind of wires, right? Which usually useful for transporting information in general. So maybe it's so that you can somehow you can use them to connect different parts of your system. They're like ballistic channels for transporting, I don't know, heat or whatever you want to transport. So maybe along those directions. So.
Yeah, maybe my naive thinking is that maybe you should try to braid this currents of edge modes rather than physically braid anions in the bulk, which seems like a very hard task in principle. But yeah, I don't know. Okay, so I do not see any other questions, and thank you very much, Rodrigo, for your very interesting presentation and everybody for participating. And we have more seminars this year, so we'll see you again next week, hopefully.
Thank you.